Can you tell me the first 6 of the first one? Who can tell me the first 6 of the first one? Seema, you have the first 6? What's S1? Sure. What's S2, Seema? 3. Oh, did I freeze this? Sorry. 3. Then what?
6.
S4? 10. S5? Nice. S6? 21. Who agrees? Is Seema popular today? Oh, you are popular today. Excellent. What about the second one? This one's slightly different. Slightly different. Anybody want to tell me what the first 6 for the second one? Just list them off for me. Can anybody list them off for me? I hadn't got that far. Need a little more time. If you plug in 1, what is it going to be?
0.
Yeah, S1 is going to be 1 minus 1 over 1, so it's 0. What's S2 going to be? 1 plus negative 1 squared over 1, so what's that going to be? Oh, 2. Excuse me, what did I plug in there? Did I plug in the right number? No, I didn't. So it's going to be 2 plus negative 1 squared all over what? 2. So what is that going to be? 3 over 2? So what about S3? So 3 plus negative 1 to the third over 3. So what's that going to be? I think someone said it. Did I hear it out there? 2/3. So can you got 5 over 4, and then S5? 4 over 5, and S6. 7. Oh, look at that. Nice harmony. I like that. What's it called? Anybody know? Begins with an E. Explicit. That's right. Explicit. Very useful. If you want the 10th term, you plug in 10. Excellent. So that was one direction, though. Let's go in the other direction. So before we had the definition of the sequence and we generated the output, what do we have here? The output, and we're trying to come up with the definition for the sequence. So effectively, this is coming up with the function. This is coming up with the function. So this is investigatory. This is using your intuition. There's no single algorithm you're going to use to deconstruct this. But the idea is, let's start with n equals 1, everybody, not n equals 0. Let's start with n equals 1. So what does 1 correlate to? 1. N equals 2 is going to correlate to 2. N equals 3 is going to correlate to 4. And you might already notice a pattern. Did it pop out to anybody?
Everything gets multiplied by 2.
Everything gets, you double it each time. So if I want the nth term by just using n, what is it going to be? Sn is going to be equal to what? 2 to the n minus 1, exactly. Why is it n minus 1 and not just 2 to the n?
The first term, like 2 to the...
2 to the
first would be
2 would be 1 off.
But for the first term, it's 1.
It's 1. 2 to the 0, exactly. So sometimes you'll notice this. What's interesting about this is if you make the assumption that this pattern continues, this would hold, right? This is also a fallacy of some standardized test questions. They're like, what is the definition of this sequence? Is this the only definition of the sequence? What I mean by that is this. If I gave you 2 points and said, how many unique lines go through 2 points? How many unique lines go through 2 points? How many? 1. There's 1 unique line that goes through those 2 points, right? But let's say I changed it a little bit. Tell me the function that goes through those 2 points. How many functions goes through those 2 points? An infinite number. It could go, you could do anything you want, right? There's your function. Similarly, you see, those are 5 points essentially. 1, 1, 2, 1, 1, 2, 2, 3, 4, 4, 8, 5, 16, 6, 32. This is one definition. This is what they're asking for, but this is one definition. It can get more fun, though. Should we make it more fun? I want to make it more fun. You don't really have a choice. So why don't you try that? If you're looking for a pattern and there's something that already sticks out as being not like one of the others, if you can do something relatively straightforward to make it look like the others, is that going to help you? Absolutely. Absolutely. Anybody want to give me an explicit definition? Anybody have one? Yeah. The back?
7 divided by 3n minus
7 divided by 3n minus what?
minus 1.
Awesome. That seems like it's... Is that perfect? Is that good? Plus what?
3.
Oh, 3n minus 1 plus 2?
3.
Yeah, so what is 3 squared plus 4 squared?
Oh.
This isn't a rhetorical question. What is 3 squared plus 4 squared? 5 squared, right? Are there other Pythagorean triples like that?
Yeah.
5 squared plus 12 squared is 13 squared. there are an infinite number of Pythagorean triples like this. There's lots of them, right? So a to the n plus b to the n equals c to the n if n is greater than 2. This right here, a, b, and c are integers. N is greater than 2, it's also an integer. There are no solutions, meaning there are no 5 cubed plus 8 cubed. There's nothing works. There are no triples that work. This was asked hundreds and hundreds of years ago, and it was famous because a mathematician wrote it down and said, I have a solution to this. He wrote it in the margins of a book he was taking his notes in, but I don't have enough space to properly write out the solution. People worked on it for 350 years, couldn't find any sort of solution. They basically decided he was either wrong about his solution or he didn't have one and he wasn't telling the truth. But it wasn't a solution wasn't discovered until proving it's not possible. The proof of proving it's not possible wasn't found until 1999. It's also 300 pages long, and probably 50 people in the world understand what's going on in the proof. So are they looking for a better one? Yes, they are. Okay, so you can go in two directions. You can either have the definition and get the output. You can have the output and get the definition. What is this? What am I looking at right here? Are these sequences? Are these sequences? Yeah, they're sequences. Here are two different ways you can visualize sequences. So in this case, what do you see here? Here is the input and here is the output. So what's one advantage to writing a sequence this way? What can you start seeing? A pattern. A what?
Maybe a function.
You can see maybe what function it approximates. What does it look like this is doing?
Yeah, it looks like it's functioning now.
What is with the C? It's converging. Have you done stuff with convergence before?
Yeah.
I think you have. Maybe a little bit. Here's another way. Is this the same sequence right here? Is this the same sequence or is this a different sequence? What do you think? You want to say different. Is it? Well, by definition, it is the same one. But it's two different ways of looking at it. See, it expanded into 2 dimensions, but you don't actually need 2 dimensions in this one if you want to just visually see what's going on here. It's bouncing back and forth around, looks like 1. So you might make the guess that it's converging to 1. Now, guessing something converges is not the same as proving. 99 is still an infinite distance away from 100. Being 99% sure of something is sometimes good enough, but not for solid proof. Solid proof. Okay, so this is what I would like you to do right now. Everybody find a place up at the board in a pair here. So you have the 2 sideboards. We're going to use the 2 sideboards. At least, let's get into groups of 1, 2, 3, 4, 5, 6. Groups of 3. So a group of 3 and then 2 groups of 3 over on that board. Get up there, and I'll give you markers in a second. How do we feel about listing terms based on recursive? So for A, anybody, oh, look at the color up there. I love it. So what do you have up there for A? I think I see 4, 7 something or something like that. What? 4, 7, 10, 13. 10, 13, 16, 19. Seems pretty good. I like that. Nice. What do we have for B here? Different group here. Do we have B? Anybody agree? What do we got for B? What is B up there? Is that 2, negative 6? I can't really. 2, negative 6, and then what? 18, negative 54, then what? 162, negative 46. You think, oh, look at that. They agree over here. The north side agrees. Excellent. Okay. So now I think it gets to the real fun stuff with recursive definitions. It's kind of fun. Anybody have a good one? Anybody have a good recursive definition? Did you all get the same?
Yeah.
So is it 2 times Sn minus, I think it was 2 times Sn minus 1, like that? And then what? Plus 1. So you double the one before and you add 1. Looks great. So here's the thing about recursive definitions, kind of like some of the calculus questions we're going to run into. You can tweak small little things and then it becomes really, really, really challenging. So let's tweak it a little bit. What do we think of this one? So if I ask one is more straightforward, the explicit or the recursive? Yeah, the explicit is great, right? Because what is the explicit? Sn is equal to what? N squared. So the real question, what's the trivial way to do it? If S1 is 1, you could say, S2 is 4, but another way to say that is, it's the last term. What do you do to the last term?
Sn plus 1.
Well, you know that each one is squared, right? Is there any way to go backwards or forwards based on the one before it? Ah, so could you square, Sn could be what? The square root of what?
plus 1, and then also. That's
Right? So look, you had most of what you needed. You had most of what you needed. You knew it's squared, right? So if you have, you go back one, you square root it, you add one, and then what do you do? Square. So if we want the fourth one, what do you do? Plug in 4, right? So what was the one before it? 9. Square root of 9 is not rhetorical, 3. Add 1 to 3, you get 4, and then you square. So sometimes having the explicit definition will get you right to the edge of one of the recursive definitions. One thing I don't quite remember is how many different recursive definitions are possible. My guess, because math usually works like this in terms of numbers of answers, there's usually 3 types of numbers of answers, like numbers of answers. Anybody know what it's mostly true. I can't prove it, but in terms of solution sets, sometimes there are no solutions. Sometimes there's an infinite number of solutions, or there's some sort of finite number of solutions. Like there are 7 solutions or 1 solution. Sometimes you have a whole lot of them, sometimes you have none, sometimes you have 7. Which category do you think I find most interesting? Finite. I actually find the cases where you have something that seemingly is natural, and for some reason there are 12 solutions. For example, I'll give you a semi-example of this. What is this? What's this? What am I writing?
The quadratic formula.
Yeah, okay. Over what's over? 2a. Okay, so that's the quadratic formula. That is the general solution to what? ax squared plus bx plus c equals 0, right? So there's a cubic, which is this, right? Plus cx plus d equals 0. Is there a cubic equation? Is there this equivalent for that? There is. There's a cubic equation. You can find, because what do cubics look like? They look like this, right? Or this. They either go up or down like that. You're always guaranteed to have one real root. You can find it using that. So there is a quadratic. There's a cubic. Do you think there's a quartic? So this is cubic. Do you think there's a 4th degree one? Yep. 5th degree, 6th degree. So what degree can you take polynomials to? Infinite. There are infinite degree polynomials, right? So theoretically, there's a quadratic formula. There's a cubic formula. There's a quartic formula, quintic, sextic. I can't do a Latin, right? Sorry, math. Well, guess what? There is no quintic. Not that they haven't found it, it's been proven not to exist. Like, wrap your head around that for a second, for a minute. Do these get really complicated? Like, is the cubic equation super complicated? Yes. Is the quartic even worse? Like, the quartic fills up a poster. It's horrible, right? Is there any practical reason to use it? No. Maybe in programming. But the thing is, there is no quintic. Is there a 6th degree one? Is there a 7th? It's super fascinating to me when nature apparently, or what I think of as nature, like skips numbers. Fascinating. Okay. So let's warm up a little bit more, shall we? Let's warm up a little bit more. Let me pause this. Sn is 2 to the n plus 1. I like that one. Oh, thank you. Hey, you learned that lesson. Excellent. It's not those classes that wait like 10 minutes and then laugh at me when I notice later. Thank you. Thank you. 8. So what do we have here? 1, 3, 7. Seems like it's 1 less than powers of 2. Yeah. Right? So Sn is going to be, what is it? 2 to the n quantity minus 1, I think. Is that good? And here's the thing. Just because you look at a solution and go, oh, that is clearly the answer, doesn't mean it's not a pain in the ass to get there. I saw things all the time when I was in undergrad and graduate school where I would see a beautiful 7-step solution, but that is awesome. I understand every part of it. And then the professor would say something like this, and my undergrad professors, some of them had deep Hungarian accents, so I tried it. What they don't tell you is it took 7 years to see those 7 lines. And he's not kidding, okay? Sometimes it takes that long. So don't be dismayed when you're like, oh, I should have gotten that. What's the worst word to see in a math textbook? Anybody know what it is? This word. Or any synonym. Any book that uses that is a terrible book. There's no point to using that word. Do you know why? Either you understood it, and it doesn't matter that they said clearly, or you didn't understand it, and it kind of hurts. It cuts to see that word. You know what I mean? It's like, I got it. Thanks for reminding me. Oh, I didn't get it. Well, thanks again. Clearly, no, it's just not true. Also, it goes to the fallibility of answer keys. Do you know who writes answer keys for textbooks? Indentured graduate students. So are they always going to be perfect? Hopefully, but no. So just because you see an answer in the back of the book, if you disagree with it, don't just, like, you can assume you're wrong and maybe try again, but don't always assume the answer key is always right. We have found errors in every textbook I have ever worked with, every single one. Okay, what about 9? Anybody have 9? 2, 5, 10, 17, 26? Anybody have 9? Oh, it's squares plus 1? So we go up? So Sn is what? N squared plus 1, like that? Huh, that's good. What about 10? 1, 3, 5, 7, 9. Oh, what are those?
Odd numbers, but then times negative.
So there's going to be a -1 to like some sort of power of n in there. It's going to be flipping, right? But then what's going to go? We want the explicit. So what? 2 what? Anybody have it? 2n minus 1. Does that map? Do the signs map properly for this one?
Nope. No.
So what do I need to do to n?
Plus 1.
+1 or what? I like that. You can absolutely do -1 if you care about that such thing. So +1, does that work? I think so. Does it get more fun with 11 and 12?
You could also like do.
Oh, are there other ways to do it?
Yeah.
Absolutely. Sure.
Or you could do like minus 99.
99, yeah. So the thing is, again, it's like the functions, right? How many different functions go through those 4 points? Like many of them, right? Great. Assuming no vertical lines there. Can you design other sequences? Absolutely. So when I ask you for answers, I would love, if possible, for you to keep them as clean as possible, just for my own sanity. Does that sound good? Just for my own sanity? Oh, I like 11 there. Do you have a clean one there for 11, Tomas?
Yeah.
What'd you get? Tell me.
Over, 2n plus 1.
N over what?
2n plus 1.
2n plus 1? N over 2n plus 1. Oh, look at that. So you noticed it went 1, then 2, then 3, then 4, then 5. Hey,
I
there's
actually had this problem on a pre-calc test 2 years
excellent.
ago.
Like, you remember that from 2 years ago?
I just like, I
Dang.
just saw it right away when I took
Nice.
the test, so.
What do you guys notice about 12? What's the numerator doing? What's the numerator doing? Flipping sign. So Sn is going to be -1 to the n plus 1. And then you have 2, 4, 6, 8, 10. Those are just what? Even numbers. Awesome. Okay. Sound good? So tonight, make sure you do the homework as posted, which also includes the tech orientation. Get that going. It should take you about 5 minutes when you have an active internet connection.